Right, okay. Guys, the last thing that we discussed is about the standard model. We spoke about the existence of putting it. Okay, we spoke about the existence of Cox and Liptons. Okay, so we told that there are 6 types of Cox and 6 types of Liptons, which are fundamental particles. So there are 12 fundamental particles, correct? Fundamental particles are particles which you can't break it down further, correct? So back then, people used to think protons and neutrons, these are fundamental particles, you can't break these. Atoms are made of these. The nucleus consists of protons and neutrons, correct? And they used to think protons and neutrons, you can't break it down further. So the latest discovery is, no, yes, you can break the protons and neutrons further into subatomic particles, which are quarks and leptons. Okay, so protons consist of quarks, neutrons consist of quarks, and electrons, you can't break it down further. It belongs to a family called leptons. Am I right? So we spoke about 6, there are 6 types of quarks and 6 leptons. Did we discuss up to this page? Yes, right? Fine. Guys, turn to the next page. Page number 7, did we go through it? Hello, people online, can you hear me? Hi. People online, hello, can you hear me? Hello. Hi, can you hear me? Okay. Did we go through page number 7? Did we? No. Right. So guys, in page number 6, you see the 6 leptons and 6 quarks. Okay. Turn to page 7. Only the first 3 quarks, up, down, and strange, were known from the middle part of the 20th century. And the charm quark was discovered in 1974. Okay. Only the first 3 quarks were known, up, down, and strange were known. And then the next one, the charm, was discovered in 1974. The symmetry of the standard model indicated to scientists that there were other particles they had never observed, which should exist, the bottom and top quark. Okay. Experiments were carried out to find these, and the accelerated experiments at Fermilab discovered bottom in 1977 and the top quark in 1995. Okay. So the last quark was discovered in 1995, around 28 years ago. Okay. Current particle theory believes that all matter in the universe is constructed from combinations of some of these 12 particles and no others. Is it? Is it? So far, yes. Okay. So in another 10 years or 15 years or 20 years, they can come up with a new theory. So according to what has been discovered so far, all the particles in the universe is made of these 12 particles and nothing else. Okay. So current particle theory. Okay. It may not be the ultimate reality, but yes, according to what is observed right now, current particle theory believes that all matter in the universe is constructed from combinations of some of these 12 particles and no other. Each of these 12 particles listed in tables A and B also has an antiparticle. Okay. These 12 particles have an antiparticle, these antiparticles have the same mass, but all their other properties are opposite to those of the normal matter particle. To write the symbol for an antiparticle, it is the same as the normal particle with a bar above the symbol. So, for an example, the charge of an anti-down quark is +1/3, and the symbol is d bar. So, guys, down quark is d. From the table C, a down quark is d, and it has a charge of -1/3. Okay, so there's something called the anti-down quark, which is d bar, and it has a charge of +1/3, the opposite charge. Same mass will be the same as the down quark, but the charge will be opposite. So for an if you take the anti-charm quark, charm is +2/3. So anti-charm quark will be having a charge of -2/3, and it will be denoted by C bar. Understood? And if you take muon, which is a lepton, it has a charge of -1. So anti-muon will be mu bar. It has a charge of +1. So there are 12 fundamental particles, and those 12 fundamental particles have 12 antiparticles, in total 24 particles. Understood? Right. In a few cases, the antiparticle notation treats it as a different particle in its own right, and the bar may not be used. The positron is an example of that. Positron is an anti-electron. Doesn't use a bar, but it is written as E+. So the electron is having a charge of -1.6, or we take it as -1. Okay, where 1 is considered as 1.6 × 10⁻⁹ coulombs. So the electron has a charge of -1, right? So anti-electron is supposed to be E bar. So it will have a charge of +1. This E bar, the anti-electron, is having a name positron. What is it? What is the positron? Anti-electron, which has the same mass as the electron, but the opposite charge. Okay. The positron, the anti-electron, doesn't use the bar symbol. It's usually written as E+. So if you see E+, that is E, the anti-particle of the electron, which is positron. Okay. Right. Turn to the next page. Baryons. If 3 quarks are combined together, the resulting particle is a baryon. I like that part. If 3 quarks are combined together, the resulting particle is a baryon. If the question is what is a baryon, what is your answer? 3 quarks combined together. Simple. What is a baryon? 3 quarks combined together. That is a baryon. Protons and neutrons are baryons. Okay. That means protons and neutrons are made of 3 quarks. Okay. What is a baryon? A particle which is made of 3 quarks combined together. So proton is a baryon, so which means it is made of 3 quarks. Neutron is a baryon, so which means it's made of 3 quarks. Protons and neutrons are baryons. A proton consists of 2 up quarks and a down quark. So this is a proton. It has 2 up quarks. 2 up quarks and a down quark. Okay. While a neutron is a baryon which consists of two down quarks and an up quark. Neutron has two down quarks and one up quark. Okay, that is something for you to remember. Proton consists of what? Proton consists of two up quarks and one down quark. Two up, one down. Okay. Neutron consists of two down and one up quark. Okay. Proton is a baryon. It consists of what? Two up, one down. UUD. Proton is UUD. Neutron is UDD. One up and two down. Correct? Okay. Right. So, what is the baryon? Baryon is three quarks combined together is baryon. Okay. Three quarks combined together is a baryon. So proton is a baryon. Neutron is a baryon. Proton consists of UUD, two ups and one down quark. Neutron consists of two down and one up quark. Okay. Right? Fine. Continue. Other baryons are more obscure and have very short lives, as they decay through a strong nuclear force reaction that makes them highly unstable. Yet other baryons like sigma, omega, and lambda particles decay via the weak nuclear force, and that is not necessary for you. Fine. So, turn to the next page. Mesons. Mesons. If a quark and an antiquark are combined together, the resulting particle is known as a meson. Okay? Tell me. What is your question? Tell me. Do you have a question? Right. So guys, highlight that part. If a quark and an antiquark are combined together, the resulting particle is known as a meson. Are you new to class? Yeah. Yeah. Okay. Fine. Is there anyone who is new to class today? If you are new to class and if you haven't done this before, this might completely sound like a Latin lesson for you. Okay, can't help. That is how it is. Right. Right. Let's highlight that part. If a quark and an antiquark are combined together, the resulting particle is known as a meson. Okay. What is a meson? Quark and an antiquark combined together is a meson. Okay. Quark and an antiquark combined together is meson. Right. The pion and the kaon are the most common examples of meson. Okay. Consist of an up quark combined with an anti-down quark. If a meson is a combination of a quark and an antiquark, the meson's charge must be 0. Correct, right? If a quark and an antiquark are combined together, the combination will have a charge of 0. This is the case for the J particle. Fine, blah, 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 blah. That is not necessary for you. You can just read that part. What you need to know from that part is what is meant by a meson. Okay. Turn to the next page. Hadrons. Quarks can interact. Quarks can interact via the strong nuclear force. Thus, baryons and mesons can interact via the strong nuclear force. Any particle which experiences a strong nuclear force is called a hadron. Highlight that definition. What is a hadron or a hadron? It is a particle which experiences a strong nuclear force. Strong nuclear force is a type of force. You call it, the name of that force is strong force. Any particle which experiences strong force is called a hadron. Okay. So quarks can experience this force. So the particles which are made of quarks will fall to the category of hadrons. Okay. What are the particles we know made of quarks so far? Whatever. No, the type of particles I'm asking. Three quarks combined together is baryon. So baryons are hadrons. They can experience that strong nuclear force, so they are hadrons. And a quark and an antiparticle combined together is meson. So meson consists of quarks. Quarks can experience a strong nuclear force. So mesons fall to the category of hadrons. So repeat that statement. Any particle which experiences a strong force is called a hadron. So baryons and mesons are both hadrons. Understood? Okay. Right. Quark is also hadron. Right. But if you take leptons, they don't experience the strong force. Leptons, the 6 leptons, they can't experience a strong nuclear force. So they don't belong to the category of hadrons. Okay. Leptons do not experience a strong force and so are in a separate class of particle from the hadrons. They are not hadrons. Is that clear? Okay. What are baryons? Baryons? 3 quarks combined together is baryon. What is a meson? Yeah. You.
1 quark and 2 combined.
A quark and an antiquark combined together is meson. You. What's hadron? Particle which experiences strong nuclear force is hadron. Correct? So who are the hadrons you know? Baryons and mesons. Do leptons belong to hadrons? Why not? They don't experience strong nuclear force. Correct? Okay. Proton consists of what? 2 ups and 1 down quark. Neutron consists of what? 2 down and 1 up quark. Okay. Correct? Is proton a hadron? Yes. Is neutron a hadron? Why? it experiences strong nuclear force. Okay. Is electron a hadron? Is electron a hadron? No. Why not? It's a lepton. It doesn't experience strong nuclear force. Fine. Continue. The four forces of nature. There are four forces of nature. What are those? There are four other particles that we have not yet mentioned here. Because they are not matter particles. They are known together as exchange bosons. The matter particles interact by the four forces of nature, which are gravity, electromagnetic force, strong nuclear force, and the weak nuclear force. These are the four forces. Okay. Each force acts on particles which have a specific property. Each force acts on particles which have a specific property, such as mass in the case of gravity, or electric charge for the electromagnetic force. The process by which these forces act has been modeled by scientists as an exchange of another type of particle. The exchange mode, this is not necessary, just read it. For example, for a proton and an electron to attract each other's opposite charge, they pass photons backwards and forwards between each other. That is not necessary for you. Just for your reference, you can just read that part, not relevant in the syllabus. Let's turn to the next page. So reactions conserve properties. As in a reaction, when a reaction happens, a nuclear reaction happens, there are few properties that must be conserved. Let's see what are those. Go through it. For any particle, for any other particle reaction to occur, the overall reaction must conserve various properties of the particles involved. The total combination of mass energy must be the same before and after the reaction. Okay. Not the energy conserved or mass conserved. Energy mass combination has to be conserved. So which means in a reaction, if the mass is reducing, equivalent amount of energy will be generated. Okay. If the mass is increasing in a reaction by any chance, that means the equivalent amount of energy will be decreased. Okay. So the energy mass combination will be conserved in a reaction. Highlight that part. The total combination mass energy must be the same before and after the reaction. Okay. Furthermore, momentum and charge must be conserved. Momentum should be conserved. And the charge should be conserved. Okay. Momentum and mass energy are difficult to check. In a reaction, particles can begin or end with more kinetic energy to balance any apparent mass difference. This is how accelerated collision experiments can create large mass particles. Accelerated collision experiments can create large mass particles. Particles with high kinetic energies can have the energy converted into mass to generate many particles with less energy. Reactions can also have similar flexibility to ensure momentum conservation. Fine. The next one, charge conservation. Go through that. Charge. In a reaction, let's say, before the reaction, there is, for example, the mass is m1 of all the particles. After the reaction, let's say the mass is M2. M1 minus M2 is the mass difference. So mass is reducing. So that for that much of mass, energy will be generated using E equals mc squared. Get it? Right. Charge conservation. Charge must be conserved for any particle interaction to be possible. We can quickly see if charge is conserved by checking the reactions equation. Consider two common nuclear reactions, alpha decay and beta minus decay. So guys, if you take an alpha decay, for an example, let's say uranium is decaying to thorium and producing an alpha particle. Okay, here the charge of uranium is plus 92 protons. Thorium has a charge of plus 90. Alpha particle has a charge of plus 2. So 90 plus 2 is equal to 92. Charge is conserved. Okay, definitely the charge has to be conserved if a reaction to be possible. And even if you take a beta minus decay, this is a beta minus decay reaction equation. Carbon is getting converted to nitrogen. So here the charge is plus 6. Nitrogen has a charge of plus 7. This beta minus particle has a charge of minus 1. And this whatever the particle is not having a charge. So the charge is conserved. 7 minus 1 is 6. So the charge is conserved. So in a reaction to happen, the total charge before should be equal to the total charge after. That is what meant by the charge conservation. The reaction for beta minus decay, it is a particle actually formed in the beta minus decay. The complete form of beta minus decay is this. Okay. Right. The reaction for beta minus decay led to the development of the theory that neutrinos and antineutrinos exist. Okay. The reaction for beta minus decay led to the development of the theory. Neutrinos and antineutrinos exist. They are almost massless and have no energy. So are also almost impossible to detect. Okay. Turn to the next page. If the same nuclear change produces the same single particle every time, then for mass energy to be conserved, the beta particles would need to have the same energy every time. This is the case for alpha particles. However, scientists found that beta particles from nuclei of the same isotope have a range of kinetic energies. This suggested that another particle was flying away with some kinetic energy, so that the total kinetic energy produced was always the same. Did you understand that? Go through that again. However, scientists found that beta particles from nuclei of the same isotope have a range of kinetic energies. Now, when a beta decay happens, the beta particle which is coming out should have the same kinetic energy. If you do the same, using the same reaction, when you repeat it, beta particle should have the same kinetic energy, right? But what are they saying is, scientists found that the beta particles from nuclei of the same isotope have a range of kinetic energies. They don't have the same energy. Okay? When you keep repeating the same thing again and again, every time you get a different kinetic energy. So which means this suggested that another particle was flying away with some kinetic energy. Okay? So there is another particle which is not only the beta minus. Exactly, yeah. Fine. Turn to the next page. Conservation of baryon and lepton numbers. Conservation of baryon and lepton numbers. We can also check on the possibility of a reaction occurring, as a reaction must conserve baryon number and lepton number. So guys, a reaction to happen, baryon number should be conserved and the lepton number should be conserved. Okay. Right. Each cork has a baryon number B of plus 103. The cork has a baryon number of plus 103. Any cork. Okay. Listen to this part carefully. This part is important. And so baryon has a value of B, which is plus 1. A cork has a baryon number plus 103. If you take a cork, a baryon is made of what? 3 corks. So if you take the baryon, what is the baryon number of baryon? 1. 103, 103, 103, which is 1. Okay. A cork has a baryon number of plus 103. A baryon is made of 3 corks. So a baryon has a baryon number of plus 1. Okay. Right. Each lepton has a lepton number of plus 1. If you take any lepton, how many leptons are there? 6 leptons. So if you take electron, which is a lepton, it has a lepton number of plus 1. Okay. Antiparticles have the opposite number. As mesons are cork and anticork combination, their total baryon number is 0. Correct? Mesons are made of a cork and an anticork. So a cork has a baryon number of plus 103. An anticork has a baryon number of minus 103. Plus 103 minus 103 is 0. Correct? Particle reaction can also occur, only occur, if they conserve baryon and lepton numbers overall. This means the total for each property must be the same before and after any reaction, or else it cannot happen. Let us revisit the alpha and beta decay to check the conservation of these numbers. Okay. So guys, if I take the alpha decay of uranium 235 Kc, charge is conserved. We already considered that earlier. Charge is conserved. If you take the baryon number, uranium has 235 nucleons. Okay, protons and neutrons. Each proton and neutron, proton is made of 2 U's and a D. Neutron is made of 2 U's, 2 D's and a U. So either way, they are made of 3 quarks. So each, the proton has a baryon number 1. Proton number has a baryon number 1. A neutron has a baryon number 1. Correct, right? The cork has a baryon number 103. So proton has a baryon number 1. So a neutron has 3 quarks. So baryon number is 1. So if you have 235 nucleons, the baryon number is 235. Correct? Thorium has 230. Where? For which one? That is for lepton. This has nothing to do with the charge. This is not the charge. This is lepton number. So what is, for a lepton, its lepton number is 1. 1 plus 1. For an antiparticle, lepton number is minus 1. If you take a positron, it has a lepton number minus 1. but the positron is charged positive. So don't get confused with the charge. This has nothing to do with the charge. Okay, fine. So guys, here, look at this baryon number. Thorium has 231 nucleons. So its baryon number will be 231. Alpha particle has 4 nucleons. So its baryon number will be 4. So baryon number is conserved. 231 plus 4 is 235. Done. If we check the lepton number, uranium or thorium or alpha particle, they don't have any leptons. So lepton number is 0, 0, 0 here. So lepton number is conserved. Understood? For any reaction to happen, the both baryon number and lepton number has to be conserved. Okay. The next one, if you consider the beta minus decay, okay, this has a charge, this has 6 protons. So the charge is 6. Here there are 7 protons, charge is 7. Here beta minus particle, charge is -1. This anti-electron neutrino, charge is 0. Charge is conserved. Done. Okay, listen. Baryon number, if you see, this has a baryon number of 14 nucleons. 14 nucleons. This doesn't have any nucleon. This doesn't have any nucleon. 14, baryon number is conserved. If you take lepton number, carbon doesn't have a lepton number. No leptons. Carbon nucleus, 0. Nitrogen nucleus, no lepton, 0. The beta minus particle means an electron. Electron has a lepton number of +1. Correct? And this is an anti-electron neutrino. Electron neutrino has a baryon lepton number of 1. Anti-electron neutrino has a baryon lepton number of -1. Correct? For any lepton, the lepton number is 1. There are 6 leptons now. For all those 6, the lepton number is 1. Go to that chart for the leptons. Here, this is electron neutrino. It's a lepton. So that means electron neutrino has a lepton number +1. Okay. So anti-electron neutrino has a lepton number -1. Electron has a lepton number 1. So if you consider the anti-electron, it will have a lepton number -1. Understood? It's a very simple theory, but it's a new theory for you. Right? So guys, before the reaction, lepton number is 0. After the reaction, the total lepton number is 0. So the lepton number is conserved, so the reaction can happen. Is that clear? Understood. So definitely, all the leptons will have a lepton number +1. Antiparticles will have a lepton number -1. Okay. Yes. Right. So in a reaction, what are the conservation? Listen. Charge is conserved. What else is conserved? Baryon number is conserved. Lepton number is conserved. And mass energy combination is conserved. There are 4 things. I repeat, charge is conserved. Lepton number is conserved. Baryon number is conserved. Mass energy combination is conserved. 4 stuff to check in a reaction. If these 4 are ticked, then the reaction is possible. If any of these is not ticked, then it's not possible. Okay. No, usually you don't get, but to what I remember, there are 1 or 2 questions. Sometimes they have given values and asked you to check the conservation of momentum. But these are what usually we check. The questions will be based on these. Right. Let's take the tute. Question number 1, page number 1. I think this is a question from this year, 2023 paper. I'll give you 2 minutes. Answer the question. Right. In 2022, CERN announced the discovery of a new particle known as pentaquark, which is made of 5 quarks. The table shows the charges on some quarks. Okay. The 5 quarks in the pentaquark are C, C bar, D, S, and U. Some scientists said that the pentaquark is made of a meson and a baryon, held together by the attraction of their equal and opposite charges. Determine the quark combination of charge of a meson and of a baryon that could make up the pentaquark. Guys, what is a meson? Quark and an antiquark. What is the quark and an antiquark we have here? C and C bar, right? So determine the quark combination and charge of a meson. So quark combination has to be C and C bar. They have left space, so maybe to define what is a meson, bro. So right, meson is a combination of a quark and an antiquark. Yes, yes. Meson is a combination of quark and an antiquark. So the quark combination I will write C and C bar. So guys, the charge is supposed to be 0, plus 2/3 and minus 2/3. So that means the baryon has to, what is a baryon? 3 quarks combined together is a baryon, right there. So the quark combination has to be the remaining 3, no? UDS. UDS. But they are talking about 5 quarks, right? So they are telling 5 means C and C bar take, they are telling the 5 quarks in the pentaquark are C, C bar, D, S and U, no? So C and C bar were used in the previous one. So that means it has to be DSU. Okay. Right. There's page number 5, question number 4.
Can you show the before question again? Okay. A muon will decay into a neutrino. A muon will decay into a neutrino, an antineutrino, and an electron or a positron. Okay. A positron is the antiparticle of an electron. State one difference between a positron and an electron. What are the difference? Electron has a negative charge, positron has a positive charge.
Okay, charge. Mention that they have opposite charge. That idea should be there. Okay. Electron is negatively charged, positron is positively charged. Explain whether the following decay would be possible. You should consider the conservation of charge and lepton number. Okay. First, let me check the charge. What is the charge of a muon? Muon particle? My charge is -1. Okay. And we have an electron on the other side. It has a charge of -1. Okay. And then we have a neutrino, electron neutrino. What is the charge of an electron neutrino? 0. Charge of an electron neutrino is 0. And there is an anti-neutrino. What is that anti-neutrino? This one, anti-muon neutrino. Anyway, muon neutrino has a charge of 0. So anti-muon neutrino will also have a charge of 0. Okay, so -1 here. Here the total -1. Hence, charge is conserved. Which one? This one? That's an electron. A positron will be with a positive sign. Okay. Okay, now we have to consider the lepton number. The lepton number. A muon will have a lepton number of +1. An electron will have a lepton number of +1. An electron neutrino will have a lepton number of +1. And the anti-muon neutrino, no? It's an anti-muon neutrino will have a lepton number of -1. All the 6 leptons will have lepton number +1. Their antiparticles will have a lepton number -1. Very simple. Okay. The words are a bit fancy and new, but the idea is very simple. It's a very basic idea. There is a hyphen. No, that's a minus sign. So which one are you talking about, the hyphen? No, this is not a hyphen. This is just to say it's the minus charge, the muon. It's a mu minus, the charge, not a bar. This is a bar. Bar will be right on top. Okay. If it is an anti-muon, it should be this. This is an anti-muon. Just to know it's a minus negative charge. Okay. Not an antiparticle. So guys, the lepton number is +1. And here +1 +1 -1 is +1. Hence, lepton number is conserved.
Page number 15, question number 9. No. Charge barrier and pions belong to a group of particles known as mesons. State the Koch structure of a meson. What is a meson? A quark and an antiquark combined together is a meson. Am I right? A quark and an antiquark combined together. Muons belong to a family of particles known as leptons. State one property of leptons. They are fundamental particles which don't experience strong nuclear force. They all have a lepton number of +1. Correct. Agreed. That's a property. Correct. So I would say they are all fundamental particles which don't experience strong nuclear force. Okay. Charged pions usually decay into a muon and another particle X, as shown by the decay equation. Okay. The student suggests that X is an antineutrino due to particle conservation laws. It's an antineutrino. Okay, deduce with the student is correct. Let's see. If I take the charge conservation, charge conservation, pion has a charge of -1. Muon has a charge of -1. So X will have a charge of 0. Correct. If I consider the lepton number, pion has a lepton number of +1. Muon has a lepton number of +1. So the X has a lepton number of 0. Am I right? If I take the baryon number, pion has a baryon number of 0. Muon has a 0. Yeah. It is a lepton, right? Pion is a meson, wait, hold on. So the baryon number will be what? Lepton number. Hold on. Meson consists of. Okay. The baryon number is 0, correct? Baryon number is 0. Lepton number is also 0. Oh, hold on. Hold on. Baryon number is 0, wait. Baryon number is 0, correct? Lepton number will be it's a quark and an anti-quark, right? A quark and an anti-quark. No. A quark has a so 0. So muon has a lepton number +1. This has a so X has a lepton number -1. X has a lepton number -1. Sorry. So what is the conclusion about X? X has a charge 0, lepton number -1, baryon number 0. So it can be an antineutrino, correct? So the statement is correct. That is also correct. Pi doesn't have a pi is made of 2 quarks, a quark and an anti-quark. So the quarks don't have a lepton number. So the lepton number is 0. Pion is a meson. Okay. Then you can write the conclusion. Hence, X is an antineutrino. Statement is correct. An antineutrino will have a charge 0, baryon number 0, and a lepton number -1. Hmm? Guys, page number 20. Question number 12, part A and B. Page 20, question 12, part A and B. K. Is it there? K or something. But no need to know. Why have they asked on me? Experiments with muons are taking place at Fermilab in USA to improve our understanding of the Standard Model. The muon belongs to the family of particles as the electron. State how the muon is classified in the Standard Model. It falls to which category? Leptons, right? Muon is a lepton. Yeah. Muon is a lepton. Which doesn't experience strong nuclear force. It has a charge of -1 and a lepton number +1. Full stop. It is a fundamental particle. Okay. A muon can be produced by the decay shown in this nuclear equation. A pion is decaying into a muon and there's an antiparticle. Anti-muon neutrino, I guess. State the names of the two other particles. This is pion. And what is this? Anti-muon neutrino. And we have done part C, correct? Which was to website states the rest mass of muon is this, which is a little over 200 times that of an electron. So we converted the mass of the muon to kilograms and compared it with the mass of a electron, 200 times the mass of an electron. Yes, we got it as 206.85. Correct, right? Yes, yes. Hold on, hold on. Here's page number 26. Question number 15. Do part B. Part B. Mass of an electron is 9.11 into 10 to the power minus 31. Are you getting the answer for the first part as 1676.8? Have you got this answer? Okay, we did this last class, I guess. No? How to convert the mass in mega electron volts per c square to kilograms. We did it last class. So guys, the question says an omega baryon has a mass equivalent to 3272 times the mass of an electron. So mass of an electron is 9.11 in 10 to the power minus 31 kilogram. So multiply that by 3272. I'm getting it as 2.981 into 10 to the power minus 27 in kilograms. That is the mass of this, whatever the baryon they're talking about. Okay, in kilograms. So now if I take the mass of that particle in mega electron volts over c square to be x, if I take it as x, to convert that mega electron volts over c square to kilograms, what do we do? Multiply by 10 to the power 6 to convert mega electron volts to electron volts. And then to get rid of electron volts, multiply by the charge of an electron 1.6 into 10 to the power minus 19 over c square, which is 3 into 10 to the power 8 square. This is how you convert mega electron volts over c square to kilograms. So x I have taken in mega electron volts over c square. So I do the conversion doing this. That should be equal to the mass in kilograms, which I found to be 2.981 into 10 to the power minus 27. Understood? Get the x subjected from this. I'm getting 1676.8, which is about 1700. Okay. Okay. Right. Then the next part, calculate the kinetic energy of one of the omega baryons. Kinetic energy of one of the omega baryons. Give it a try. Okay. Now, before the collision, each particle had an energy of 14.5 giga electron volts. It's a cap. Now these collide, and then the total energy is 14.5 plus 14.5, which is 29 giga electron volts. So after the collision, we can find there are two particles produced. Their mass is this much. The mass is this much. So you can use E equals mc square and find the energy corresponding to that mass. Now let's say for an earlier it was 29 giga electron volts. No? So let's say that these mass corresponds to, for an example, of an energy of 20. Then where is the remaining 9? That is kinetic energy of the two particles. I repeat, listen. Before they combine, they had an energy of this electron, and the positron had an energy of 14.5 giga electron volts. So total is 29 giga electron volts. After that, the two particles produced are 2 omega particles. We know their mass, so we can find the energy corresponding to that. If that is, for an example, I told if it is 20, there's a difference of 9 giga electron volts. That 9 will be the energy of those particles. Understood? Give it a try. Correct. They ask you for 1. If you take the mass of 1, then you will be getting the energy of 1. But there are 2. Each. Correct. Then straight away that will give you the energy of 1 baryon. Okay, guys, listen to me. There are 2 particles, positron and electron. Each particle is having an energy of 14.5 giga electron volts. Listen to me. So before the collision, the total energy is 14.5 giga electron volts. I'm converting into joules. 14.5 into 10 to the power 9, and then 1.6 into 10 to the power minus 19, 2.32 into 10 to the power minus 19 joules. Okay, that is the energy of what? 1 particle. So before the collision, what is the total energy? 2 times this. This is the total energy before the collision. correct? After this collision, there are two particles produced. No? Those two particles have a mass of 2.981 into 10 to the power minus 27 kilogram. So the energy corresponding to that mass is using E equals mc square. I found 2.6829 into 10 to the power minus 10 joules. Okay, that is the energy of the mass corresponding to one particle. So there are two of those. No, so those two will have an energy twice of that. Correct. So this difference will give you the kinetic energy of the two particles produced. Do you understand that? The total energy at the beginning minus the energy corresponding to the masses produced will give you the kinetic energy of the two particles. Because mass energy combination is constant, conserved. So initially we have a certain amount of energy that should be equal to the mass plus energy after the collision. So the energy corresponding to the mass is this 2.6829 into 10 to the power minus 10. That is for one particle. And there are two particles. So twice of that. Understand? So this difference will give you the kinetic energy of the two particles. But they are asking the kinetic energy of one particle. So I will again divide this by 2. Am I right? So which is basically going to be E1 minus E. That is going to be 2.32 into 10 to the power minus 9 minus 2.6829 into 10 to the power minus 10, which is 2.05 into 10 to the power minus 9 joules. Have you got this answer? They are asking the kinetic energy of one of the omega baryons. So I have multiplied that by 2. 14.5 is the energy of one particle. And then I found it as E1. This is the energy of one particle. So when I did my calculation, I have taken twice of that as the initial energy. Okay. That also then you have to multiply by 2 because I use E equals mc square. M I have taken the mass of one particle, one omega particle. So then 2 of that is then multiply that also by 2. That will give you the kinetic energy of the two particles produced. But they are asking the kinetic energy of one particle produced. So again, divide that also by 2. Correct. But I'm just telling you the big picture, what's happening here. If you do understand this minus that, that's fine. Huh? Kinetic energy is what produced, okay. Energy loss is what converted to mass. You can ask me your question. At the beginning, there was kinetic energy. There was energy. After that, there is mass and energy both. So we know the mass. So I found the energy corresponding to that mass. That subtracted from the initial energy will tell you how much energy how much kinetic energy these particles are having. Okay, understood? Correct. So that energy mass duality remains constant. That is the theory.
Okay. Right. Right, because you can go for a break. See you in 15 minutes.
Okay. A student correctly suggests that this collision cannot lead to both particles be omega baryon, as this breaks a law, a conservation law. Discuss the student's suggestion. Okay. Guys, right, a electron and a positron. Electron and a positron produce two particles. No? I'll take the omega particle as omega is a baryon. Okay. I will just take it as X and X, let's say. Look at this, look at this. Guys, if you consider the baryon number conservation, before this happened, before the collision, what is the baryon number? An electron and a positron. Positron has a baryon number how much? 0. Positron has a baryon number 0. So before the collision, the baryon number is 0. Correct? So after the collision, if omega is a baryon, if both are omega, baryon number will be +1 +1. The total baryon number will be +2 after that. Can that happen? So which means one has to be a baryon and the other one has to be a antiparticle of it. That way you can get +1 and -1 here, which will make it 0. Okay, so the student is telling that this collision cannot lead to both particles being omega baryons. One has to be the omega baryon, the other one has to be the antiparticle of it. Understood? Right under that. Before the collision, the total baryon number is 0. Before the collision, the total baryon number is 0. So after the collision,
So can you repeat?
before the collision, total baryon number is 0. So after the collision, total baryon number should be 0. Okay, full stop. If both are omega baryons, if both are omega baryons, after the collision, total baryon number will be 2. After the collision, total baryon number will be 2. Full stop. So one has to be be an omega baryon, one has to be an omega baryon and the other one has to be the antiparticle. Okay, charge is conserved, but if you take a baryon, how do you know the charge of the baryon? Yeah, it can be neutral as well. If you take neutron, it is a quark. It has 3 quarks, but it has 1 up and 2 down. It is neutral. Charge is 0. Just because baryon, it doesn't have to have a charge. It can be neutral as well. Okay. So the charge conservation, we can't tell it exactly. But baryon number conservation, definitely we can speak about it. Got it? Okay. Guys, the previous question that we did, the previous part 2. You understood what I told, right? Okay. Now, the previous part, we have to find the kinetic energy. Now, listen. I found it in joules, no? But the question doesn't specify a unit. Okay. Now, listen to me carefully. I could have done it easily with a different unit. Look at this. In a particle collider, positron and electron collide. Each particle had an energy of 14.5 giga electron volts. So then what is their total energy? 29 giga electron volts is the total energy at the beginning. Am I right? After the collision, the 2 particles produced are what and what? Show that the mass of an omega baryon is about 1700 mega electron volts over c square. The mass of the particle produced after the collision is, let me take, I got 1677 mega electron volts over c square. This is the mass. Okay, listen to me carefully. So this mass will correspond to an energy of how much? 1677 mega electron volts. You understand that? Why? E equals mc square, right? So if I cross multiply this m with c square, that straight away gives you the energy, which is 1677 mega electron volts. Understand? I repeat, this is the energy of the 2 particles at the beginning. This is the energy of the mass produced, of the mass. Energy equivalent to the mass. But that is for one mass, one particle. So, what if I tell you the kinetic energy generated is 29 giga electron volts, which is 29 into 10 to the power 6 electron volts, minus 1677 into 10 to the power 6 electron volts into 2, because there are 2 particles. This is 10 to the power 9. 29 into 10 to the power 9 giga electron volts, minus 1677 into 10 to the power 6, and that into 2. This will give you the kinetic energy of the 2 particles divided by 2 This will give you the kinetic energy of one particle in electron volts. You understand that? Shall we confirm it? 29 into 10 to the power 9 minus 1677 into 10 to the power 6 into 2 divided by 2. 1.2823 into 10 to the power 10 electron volts. If you want to compare this with that, multiply this by 1.6 into 10 to the power minus 19, you should be getting that answer what we got earlier. Okay. Since they haven't specified the unit here, we can get either. What was your method?
Where the energy of mass, the particle, kind of that is equal to the mass, energy mass.
This one. Correct. But you also have taken it in joules. So my point is, if you don't involve joules, I feel it's a bit easier. No? Yeah. Take down that as well.
So why did you divide it by 2?
Because they are asking the kinetic energy of one particle produced. The difference will give you the energy of both the particles. Definitely. Okay. Right. Here's Mark, question number 17 for homework. Energy. Where's turn to MCQs, page number 51. Question number 4, page 52. Okay, in a beta minus decay, okay, leave that video. Question number 6, question number 6. Question 6. Which of the following is a fundamental particle? What is the fundamental particle? Neutrino. Neutrino is a fundamental particle. Page 53, question 8. Page 53, question 8. The table shows the charges of up and down quarks. Which of the table shows the structure of protons and neutrons? Proton is 2 ups and 1 down. Neutron is 2 downs and 1 up. The answer is C. Leave it. We didn't do that. Question 16, 17. 16 and 17. Okay. Which of the following is a fundamental particle? Once again, neutrino. A proton collides with an antiproton. A proton collides with an antiproton. Which of the following could be produced by this collision? Proton and an antiproton. Consider the conservation of baryon number. Ion is a what? A meson. So that has a baryon number how much? Meson is a quark and an antiquark. No? So meson will have a baryon number 0. A proton has a baryon number what? 1. Antiproton has a baryon number -1. So if a proton and an antiproton combine together, proton has a baryon number 1. Antiproton has a baryon number -1. Total baryon number is 0. Correct? So the particles produced should also have a baryon number 0. So what could it be?
B.
A. Neutron has a baryon number of 1. No? It can't be A. Baryon number, no, it can't be A. It can't be B. Proton has a baryon number of 1. C or D? The problem with C is baryon number is okay, but electron is coming into the picture. No? So if you bring the electron into the picture, there is a lepton number of 1. Lepton also has to be conserved. So I reject C as well. So then we are left with D. D is possible. Both meson number and lepton number are conserved. What is the question? Interesting. Do it. Question 22, baby question. Even your granny can do this. Mass is the same. Charge is the negative of a proton. B, right? $25. $25th one. Table shows the relative charges on up and down quarks. Which of the following could be the quark composition of a baryon with a charge of plus 2e? What is a baryon? 3 quarks. So can it be B or C? No. So if I take, we are left with A or D, right? So if the two D's combine together, the charge is going to be minus E. If two U's combine, if 3 U's combine together, it will give you a charge of plus 2E. The answer is D. Correct? 27th. Which of the following is the quark structure of a pi minus particle? A pion minus. Can it be A or B? B. Pion is a meson, right? Which is a quark and an anti-quark. What should it be?
C.
C. An anti-up quark has a charge of minus 2 over 3e. I'm checking the answer C. An anti-up quark. A down quark has a charge of minus 1 over 3e, which will give you a charge of minus e. That sounds right. The answer is C. Guys, mark a few more for homework from MCQs. 29. 35. No. You are supposed to know that up and down quark charges. 37. 38. 42. 47. That's enough. That's it for the day. See you next week. Bye. Take care. And probably we'll be done with this next week. And we'll start with Unit 5, the following. Bye. See you. Take care.
Thank you, sir. Bye.
Bye. See you.